All right. So our discussion was quantization, and we have seen a method which gives us an optimum quantizer in terms of finding the optimum intervals and the optimum representation points inside those intervals. And the number of intervals is essentially determined by the number of bits that can be used. And we call it the Lloyd Quantizer. We called this thing the Lloyd max iteration. And as a result, we obtained the Lloyd Quantizer, the optimum intervals and the optimum representation values within the interval. Now, if we extend the idea of quantization to multiple dimensions, what we obtain will be called vector quantization. So let's talk a little bit about this thing called vector quantization first, and then we will also see the methodology to optimize them and where it works better than another case. So our new topic is vector quantization, abbreviated as VQ. All right. So it was our previous definition that the quantizer contains an encoder and a decoder. The encoder is the thing that produces an index, right? So if the input is not in the form of a scalar, it can still produce an index. Suppose that the input is, let's say, containing 4 samples, like a 2x2 region of an image, for example. It doesn't have to be like this. It's just an ensemble of some scalar numbers in the form of a vector or a matrix or just an ensemble, okay? Something like that. But in general, we are going to say it's a vector. And there is an encoder which produces an index to this input. Let's say that the input was X. Okay, so this is the encoder, and the encoder, as you see, is generating an index which is an integer number. So it's not really reconstructing the vector in any form whatsoever. It is the decoder essentially that generates a representation of this index in the form of a representative vector, decoded vector. We can say that the output of the decoder is, let's say, oops, excuse me, just jumped, yi. This yi is a vector among the so-called, so let me write it that way. It's a vector among the so-called code vectors. Among code vectors. So we call it a code vector, and that code vector ensemble is known as within a terminology called code book. So we need essentially a code book inside the encoder and the decoder. They just have the same things. One of them is just indexing the code vector inside the code book, which is the encoder, and the other one is showing the code vector with that index inside the code book, and that is called the decoder. So if we look at the encoder, actually what we have is a set of code vectors like this, consisting of essentially y1, y2 up until, let's say, yn, if there are n code vectors. This we call a code book. This one is a code vector. And what the encoder is doing is quite simple, actually. It's just measuring a similarity between the input x, and one by one the code vectors inside the codebook, looking at their distances within some matrix. And those distances will give us a minimum within the codebook. At a minimum, at one of those code vectors, it will give a minimum distance. How can we really write that kind of thing? We can say that the encoder I is essentially the overall case, the argument that gives you the minimum of the distance between x and yk. So whichever I is this, it will generate that I. And then the encoder is essentially an easier task because it doesn't even require a distance operation or anything. It just does this. Inside it, we have, again, the same code book. So we have y1, y2, all the way up to yn. So whichever I we have, it outputs that yi. Okay, if the input is I, then it produces yi. It picks the ith element in the code book, in the same code book. So this is the same code book. So this is called vector quantization, and it gets particularly beneficial to use it in the form of, or the quantization in the form of vector quantization by first combining the items. If there are some relations in between, if the combined things have relations to one another, and they usually do, right? From predictive coding, we know that the consecutive neighboring samples have correlations, and because of that, we can make predictions, predictive coding, so the prediction error is small. And what we are really trying to do in this first stage is to eliminate the correlation at the output. The output will be uncorrelated. Okay, uncorrelatedness at the output of the first stage is the critical step, so that we don't have to use vector quantization. But if you do have a vector quantizer at the output, actually you can still leave the input to be correlated, so that that correlation is handled inside the vector quantization. In that aspect, for lossy compression, a vector quantization is something more like a universal compressor, a universal encoder, because it handles the correlation of the input, and it quantizes them all at once. And since the output is it will become unrelated to one another, there is no need to further apply a Huffman coding to the index vectors of index elements of I. So VQ by itself is enough in some cases. It's a universal compression methodology in that aspect, but we will still be using quantizers in between the prediction or transformation that we will see, and in between there is a quantization, and at the output of it we still have a lossless coding system. So now how can we proceed with the optimality and the beneficial situations? One example that I want to show you for the fitting of vector quantization is the weight and height of people. Suppose your vector contains two elements. So this is your input, the x vector, which is consisting of height and weight. Now, there is a statistical relation between these two entities. But anyway, we can, for instance, quantize the weight into some quantization intervals, like from 60 to 65, 65 to 70 to 75, 80, 85, 90, etc. It goes on like this. And the height is like 1.6 in terms of meters, 1.625, 1.650, 1.675, 170, 1.725, 1.750, etc. Okay, you get the point. And it goes on like this. So the height and weight are quantized separately. That's called a scalar quantization. If you quantize the height and the weight individually, that means scalar quantization. And if you ensemble those scalar quantizations into a vector, then what you really get could be considered as forming a rectangle or a square grid like this. So this is the quantization for the weight, and these are the quantizations for the height. Okay. So essentially what you have is something like this, a rectangular or a square grid form of making quantization intervals. And the representation values are, let's say, the central points of these rectangles, okay? The center point of this rectangle, for instance, I will use a different color here. For example, this point, okay? It's just a representation. Let's say it's 77.5 kilograms, and the midway between 1,675 and 170. If we are utilizing all of these blue points in the centers of these rectangles, then it's fine. Then making a scalar quantization or a vector quantization does not really change anything. This is a vector quantization by itself, by the way. If you have, for example, n intervals in the weight and m intervals in the height, then the total number of vector quantization intervals is n times m, right? So we have n times m intervals. It's not an interval, but it's a two-dimensional interval. So n times m many indices are necessary, or you can say that we have n times m code vectors inside our code book. It's the size of our code book. But suppose that the weight and height are related to one another, and if the height of a person is within a range, then the weight of a person is also within a certain range which is related to that. And correlations usually exhibit themselves, show themselves in the form of some linear strip, okay? In that strip, the outputs occur, or an ellipse, which is just suppressed a little bit. So let's say that the blue points that we essentially encounter are these. So there's a relation between weight and height, like this. And we don't have any occurrences of people which are too high, but not with a lot of weight. For example, 2 meters tall, but the weight is 60 kilograms. That never happens, right? So we don't have any point around here, which are tall people, but they have only some kilograms between 60 and 65. There's no such people over there, for example. Okay, that's the numbers may be quite inaccurate. I'm just trying to give an example over here. Or if the weight is too much, then the height is usually in the range of being tall. So if you are too short and too fat, then of course you don't fit into this category. Or if you are too tall but you are very skinny, you're about to die, it means. Anyway, so if you have these blue points, or if the people in the community, in the population, fits into these rectangles that are shown with a blue dot in the center, only these, then we don't really have n times m intervals. So we don't really need to make expressions of these empty points, empty intervals. We don't have them. There's nobody over there. So why are we trying to quantize or construct a code book which contains code words from here? That would be inefficient. So the inefficiency is reduced by only considering the full places, and those full places we can write into the code book. So let's only use full intervals in the code book. Then the code book will contain a 2x1 set of vectors. Let's call it the code book. And the index that is necessary to represent anything inside this many, let's say, k code books is equal to logarithm base 2 of k, which may be essentially less than, or k may be less than n times m. And as we can see here, it's essentially less than n times m. N times m is this many, and only these are the intervals that we are using. This is an advantage of using a vector quantizer. And this is just an example. There are several other cases that this example can be described. And once the code book can be arbitrary like this, or since the code book can be containing arbitrary regions like this, then why should they be bound to become rectangular? They may be other shapes too. So the vector quantization helps us to split the information into or the information space coordinates into regions which are not necessarily square or rectangular. They can be just anything. For example, we may have this as an output, this as an output. I'm just trying to construct an example at this point, but I'm not sure whether I will be successful or not. Well, the number doesn't really matter. Suppose that in 2 dimensions, according to an axis, in 2 dimensions, these are the code vectors. I have 1, 2, 3, 4, 5, 6, 7, 8 code vectors. And therefore, I will be representing these code vectors using 3 bits only. The representation will be 3 bits, but the code book is necessary in the decoder side to get decoded. So the decoder needs the code vector 2. That's a side information that must be carried to the decoder side. but the compressor will compress into 3 bits. The encoder will encode according to the nearest neighbor rule again. So the encoder will still apply nearest neighbor. And when you apply the nearest neighbor, you notice a phenomenon which is called construction of convex cells. So the cells must be convex. I will explain what do we mean by convex. The nearest neighbor, for instance, if you consider this code vector and this code vector, which code vectors will be encoded by the representation of this code vector? The ones which are nearest to that, right? If something is nearer to this code vector, then if, for example, if you are here, then it will be encoded according to this. So the encoder boundaries will decide according to the nearest neighbor, will automatically induce a situation like this. I will put it in a dashed form. I will draw a line, straight line in between these two considered points, and that straight line defines the boundary between these two code vectors. If you are to the right of this boundary, then they will be encoded to the right one. If it's to the left, if your input is to the left of this boundary, it will be encoded as the one at the left. But I'm putting it in the form of a dash because other in-between lines must also be constructed for each code vector pair. For example, the one between this point and this point must be drawn like this line, or the one between this point and this point must be, sorry, drawn like this line. As you see, the lines are perpendicular to the line that are connecting those 2 points. You connect those 2 points, you find the center point, and you draw a perpendicular as the boundary, like this, like this, like this, like this, or this, or this, or this, or this, or this. Okay. So I have drawn them in the form of a dotted line. And when you combine those line candidates, the boundary candidates, in their intersection with the other boundaries, when you combine them, what you should, I may not be very accurate about this drawing, but what you should get is expected to be something like this kind of a situation. Oh, sorry, that is clearly untrue, but more like this. And like this, maybe. I don't know. Something like this. So it looks like the soap bubbles that merge together and form some shapes. Such shapes are having a property, or they satisfy a property called being convex. So the regions are always convex. A convex region is a region where, for instance, this shape, which is a convex shape, the definition of convex is like this. If you have any point inside this convex region, it may even be in the form of a set, a convex set, we can say, and any other point in the set or the convex region, and you combine them with a line. You draw a line. Suppose that the name of the first point or the coordinate of the first point or the value, the vector corresponding to the first point is A, and the second point is B. So the line in between can be written as lambda times A plus 1 minus lambda times B. Of course, if lambda is between 1 and 0. If lambda is equal to 1, if lambda is equal to 1, then lambda A will depict only A and nothing will be from B. So you are around or you are at the point of A. As you decrease lambda from 1, then 1 minus lambda will start to increase. So the blending of A and B will go towards B. And when lambda is equal to 0, it has nothing from A, 0 times A, and 1 times B. So you arrive at the point of B when lambda is equal to 0. So this kind of an in-between line can be drawn with this formula. So lambda times A plus 1 minus lambda times B will be inside the convex shape. If it stays inside, then let's call this all of these points as C sub lambda. Then we can say that as a definition, C sub lambda is an element of the convex set of, I don't know, an index, whichever. If it belongs to the set for all lambda between 0 and 1, then we say that this set is convex. That's the definition of convexity. And when you apply vector quantization, if you draw the regions of a vector quantizer in multiple dimensions, they will give you these so-called convex shapes. If it is three-dimensional, then it will be convex volumes, of course. Then it will be more like the bubbles, soap bubbles that merge together. And in the center, you notice that these are the shapes that is performed. Still, you pick any 2 points inside the convex shape, and the line combining these 2 points will stay inside the convex shape. For example, this is not a convex shape, because if you pick this point and this point, when you are drawing the straight line in between, this stays outside. So it's not convex. This kind of a shape is not convex. Convex shape. In 2 dimensions, let me say in 2D, convex shape sets are called Voronoi cells. So essentially what I have drawn here in this blue figure are a set of Voronoi cells. You may ask, what is the boundary for the ones that you draw as without ending? They don't seem to combine. Yeah, they don't combine. They go all the way through infinity. So the size of that convex cell is essentially infinity, but it is still convex. If you choose any 2 points inside the cell, it will they will be inside the same cell. So they are still convex. Of course, since the number of regions that I have chosen are too few, like only 8 regions, they will be small like this. And you will only have probably one compact and bounded cell, and all the others will extend to infinity. But if you have more and more such regions, then some parts will form still convex shapes. Like this. So as you see at this point, let me also use this one. So this could perfectly be the output of a vector quantization in the form of regions in 2 dimensions. So this is a 2-element vector quantization because that's the thing that I can draw. I have only a flat surface to draw on, so these are the 2-dimensional things that I can illustrate. I cannot make illustrations for higher dimensions, unfortunately, but these seem to be convex, and some of them are bounded, some of them are extending to infinity. And the number of code vectors it corresponds to is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, maybe. I don't know. I don't keep track of it. Yeah, whatever. So as you see, if the number of code vectors is more, you will have such awkward and interesting shapes. As a matter of fact, I would like to show you where was it? Yeah, I found it. I want to alter the screen sharing. I don't know how to do that. Now I will try. Okay. Now, are you able to see the web page that I'm showing you?
Yes, we can see.
Yeah, you can see that. So as you see, this is a Wikipedia page illustrating vector quantization, which are excellent and very nice resources that you can always consult to. The thing that you can see at the right-hand side, which is an example of a codebook of a 2D Gaussian distribution. It contains 2 Gaussian elements, which one of them is x1, the other one is x2. And this is the one that is obtained using 16 code vectors. What you can notice, and this is a very nice example, by the way, you can notice a few things. It is an optimized, in a sense, optimized sort of quantizer using numerical optimization techniques like the Lloyd Max quantizer that we are going to see right now. What you will see is that the more probable dots in the center have smaller convex shapes. As you see, all the shapes are convex. And as you go away from those dense, more probable points, the size of Voronoi regions start to increase. Okay, the regions grow. So this is also a way of making an illustration regarding what the Voronoi pixels may look like. Now, I want to proceed with this metric of codebook quality, because this metric of codebook quality automatically describes what kind of regions you're supposed to obtain. But I'm not going to proceed from this point because it's only using the square distortion. We can also use other distortion matrix too. So I will go back to my page. I hope it does. Okay. So these are what the Voronoi cells correspond to. Voronoi cells are, of course, valid for 2 dimensions only. If you have higher dimensions, you can have just convex hyperspaces. That's what you can say. I said that I will be talking about the quality setting, but for that, we have to first see the optimization methodology, because the quality or the distortion is a metric that is used together with the optimization. So let me start with the optimization first. Optimum VQ design, the vector quantizer design. What we do is we iterate again like the Lloyd iteration, but it's just one way of starting to make optimization, because in multiple dimensions things are not as easy as doing a scalar Lloyd max iteration because of the so-called convergence issues, and I will mention about those. So you start with initial set of code vectors. Then you calculate regions. Or assign sets using nearest neighbor. Okay. You don't really have to explicitly draw these boundaries. Those boundaries are just virtual boundaries, which are explaining which points will fall into which representation value. For instance, if you are inside this thing, this set, then this point here is nearest to this central representation, initial set of code vectors, a code vector, this code vector particularly, then it is assigned to be belonging to this set. And the set boundaries are just some virtual way of putting things. You can simply assign and obtain ensemble sets of input data, which is represented all together to be represented with an index I, let's say. These are the data that will be converted into I. Then I can say that this is 0, so this is 1. Then at 2, what you do is you calculate code vectors inside the regions or inside the sets. What do we mean by that? I said that all these red data points are nearest to this blue point. So they are put into the same set that is represented with this blue point. But now I have to recalculate the blue point because I have to find the average of these red dots. So here it's like the Lloyd iteration in a sense that I'm averaging the inputs, and the average, let me also indicate it here. by averaging, finding the mean. And let's indicate the new mean point to become somewhere here. So as you see, the average of these red dots are a little bit slanted to the left side. So we now have a different green point. And similarly, the blue initial center points of the other sets may also move a little bit. So these were the blue points, and they may move according to the average of the data which belong to the same set. So they may essentially move a little bit. Okay, I'm just drawing some random arrows here, but it doesn't have to be correct, of course. So these initial blue points move to the new set of code vectors, code vector positions. And when they move, and they all move, we can, oops, sorry. At step 3, go to 1. If the previous code book, let's say CI -1, and the new code book difference is not small. So if the movement is a lot, we can continue with calculating the new regions, because since the centers are different now, the regions change. So the set belonging, set membership of these red input dots will change. For example, probably let's focus to this particular red point here. It was close to the boundary, but it was belonging to the set of this one. But as you see, it moved to the left a little bit. And let's assume that this thing didn't move to this direction, but I want to make it a little bit different. So this point essentially moves a bit towards this direction. So now, as you see, the new location of this blue point will be somewhere here, and the new position of the center will be somewhere here. Probably this point will now belong to this set, okay? So the membership changes. So when the membership changes, the averages also change again, because we are averaging the points which belong to this set, and the members of those or the red dots now may include something from here because of those movements. So we have a new set of input data for this class. Therefore, the center of the class will have to be recalculated, and maybe it will move again from here to here, and then from here to here, etc. It will move a little bit, and the others will also move. Every center, every code vector will continue to move again and again and again. They will just move, and then they will stabilize. After some iterations, they stop, literally, because there are finitely many data. They will just stop. If there are a huge number of data that you are handling, you may not want to wait for them to stop. But if the difference between the previous positions and the new positions are small enough, you may stop like that. So that's also a possibility. So you continue the iteration of this thing by calculating the regions and assigning sets using nearest neighbor, calculate the code vectors, and then go to stage 1 if these code vectors are two different from the previous code vectors. You go here, and from the new code vectors, you calculate the regions or assign the sets using nearest neighbor again, and then you recalculate the new code vectors again. Do they change? If they change, you go to 1 again and again and again. This is also called the Lloyd max iteration. And there used to be quite a nice animated GIF on the internet, and I looked for it, which was showing the optimization, the small motions, as well as something else that I'm just going to explain right now. But I couldn't find it on the internet. It seems to have gone, and I feel sorry for not being able to download that animated GIF or the video before it was removed from the internet. Somehow it just disappeared. Like it was very, it was a nice one. So for those of you who may be still looking for some project ideas, that may be the project. And in 2 dimensions, you may ask for input data, just by clicking maybe on the phone, you click on the points, or you may feed the data from a file as an input, and you may ask for the number of bits to quantize, and you may run the so-called Lloyd max iteration together with a further optimization that I will indicate. And that further optimization is like this. It's because of this. If you start with an initial condition, with any initial condition, sometimes some of the cells, for example, you may start with a uniform quantizer initial condition. Okay, it makes a lot of sense, right? The starting point and the ending point, and you split it into so many regions. For instance, suppose that I give you 6 bits for the representation of the vector quantization. So you will construct 64 regions. 2 to the power 6 is 64. 64 regions. You may start by assigning horizontally, in 2 dimensions, of course, horizontally 3 bits, which is 8 levels. So you split this into 8 intervals, and 3 bits to the vertical, which is also 8 levels. Okay, like this. And then if you construct the grid here, you will have 64 regions. Right? Makes sense. And the total number is 3 plus 3 equals 6 bits. But you could assign for the first horizontal thing 4 bits, and therefore 16 regions. And for the vertical, you can assign 2 bits, which consists of 4 regions. They will also give you 64 regions, or some of the regions may be inappropriate. And once you run the so-called Lloyd max iteration, you may encounter this situation here, where some of the regions get empty. So you're not really using 64 regions anymore. You're actually using something less than that, maybe 40 regions or something. But you could split further some of the regions in between into 2 or 3 or 4 regions more to better exploit, utilize the number of bits, 6 bits. So you have the 6 bits and you want to use them, but the Lloyd max iteration give you only 40 regions then after the optimization. So that's a problem, and that problem needs to be resolved. And the best way to resolve the problem of initial condition, we come up with a new, it's not a new, it's an additional technique on top of Lloyd max. It's a technique called Linde-Buzzo-Gray. And since Gray is the only person that I know, I'm not sure about the pronunciations of these names, Linde and Buzo. If they are pronounced different, I'm sorry for that. And it's also abbreviated as LBG, Linde-Buzo-Gray algorithm. And that's it's an extremely nice and neat way of doing an optimum or designing an optimum vector quantizer without any problems of initial conditions or whatever. And it runs like this. At stage 1, start with you start with 0-bit quantizer, which is something like this. Let me first put a few data here, like this. And which I draw miserably. I'm sorry about that. So the 0-bit quantizer essentially means that you have 2 to the power 0 elements in the code book, which is 2 to the 0 is 1. You have only one representation. Which representation would you choose then? Of course, you would choose the one or the center point of this. So the code book contains only one code word, let's say C, which is the average of xi. So that's your code vector for 0-bit quantizer, and it is optimum. There's no problem about that. Then at stage 2, you come up with a random epsilon vector construct, or just create a random vector epsilon, random and small. This must be quite a small thing, and its size, its smallness, and its structure can also be perturbed a little bit. You can work on it a little bit, but for the time being, I will just say that it's a random vector, and I start with in the next iteration starts with now 2 vectors corresponding to a 1-bit quantizer, right? Which is like this. Let's call this C0. So C1, 1. The first of C1 is C0 plus this epsilon, and the other one is C1, 2. It's not a square, it's just a superscript I'm writing, is equal to C0 minus epsilon. So I'm adding and subtracting these two this random vector, and so I have now 2 vectors, and these 2 vectors, when you focus to here, they will be like this. If this small green arrow is my random epsilon, random vector epsilon, the new vectors will appear here and here. 2 purple points that we have. Very well. But then now what? I have constructed 2 vectors. Then step 3 comes into the picture, and that is run Lloyd max iteration with 2 bits. Oh, sorry, 1 bit and 2 vectors, 2 code vectors. When I run this Lloyd max, this will move, and this will move, and eventually it will draw or correspond to a boundary in between the 2 new points. I want to indicate them like this. This moves to, let's say, here, and this moves to somewhere, let's say, here. So the purple points become the black points, and therefore the central point between these two new black points, the purples become black, will be like this. So it splits the region, as you see, into two parts. And these two parts will naturally become balanced. I mean, the number of, probably the number of dots on the left-hand side and the right-hand side will be quite similar to one another. So this will become the optimum one-bit quantizer. And the Linde-Buzogray approach to this algorithm is like this. It runs like this. It goes to, oops, sorry. Let me make it solid and the stick again. At step 4, you again construct, you essentially go to 2, which constructs a random vector, but this time for each new point, or you can use the same random perturbation for each point too. Now you have, as you see, this one, the new optimized C11 and C12, because they changed, they altered in the after the Lloyd max iteration. When you go to this stage again, the next step will be like C21 and C22 will be C1 1 plus epsilon, and C1 2, sorry, excuse me, it's not like that. It's C1 1 minus epsilon, and I will have other vectors like C23, which will be C21 plus epsilon, and C24 will be C2, no, what am I doing? C1, the subscripts and superscripts are messed. Sorry about this. I will erase this. My notation was C1, 2, and this is again C1, 2 minus epsilon. What I'm saying is, again, I will focus to here. I will split these black points here into 2 points each. So these will be split into 2, like this and this. And this will also be split into 2, like this and this. So that now I have 4 points. And when I automatically run the Lloyd max iteration after step 2, if I run the Lloyd max iteration at step 3 again, those 4 points will move and they will occupy a place on the plane again, which is optimized for 2-bit or 4-level vector quantization. And then I go to step 2 again, which means each of those 4 pixels will be split into 2. So now how many new points do I have? I have now 8 points. And according to those 8 points, I will run Lloyd max iteration again. I will continue this. I will go to 2. Oh, it's too thin. As long as bit rate is not satisfied. So first I started with 0 bits, and then I proceeded with 1 bit by splitting into 2. And then I put another bit, making 2 bits, which means I'm splitting every point once again. Then I can proceed to 3 bits, which means every of those 4 points can be split again, and now I have 8 points. And every time I split, of course, I run the Lloyd max iteration once again. So I increase the number of bits one by one, which means I'm splitting all the points into two again and again. So split and then optimize, split and optimize. That is called the Linde-Buzot-Gray algorithm. There are, of course, many additional things that you can do on the Linde-Buzot-Gray algorithm, like they are mostly in terms of how to construct this random and small vector. For example, if your data is like this in the group, then a group, and it is represented with a red dot in the center, and you want to split this. How would you like to split this into two? You would like to choose epsilon in a direction in this way, right? Because if you split in the vertical directions, after Lloyd max iterations, it will probably converge back to these places, but it may take some longer time. So before running the Lloyd max iteration again, why don't you split it into a direction where the most variation occurs? Okay, and it's possible to find this direction, by the way, using linear algebra. You take a look at the 2x2 autocorrelation, or the autocovariance. Actually, it's not R, it's C. If you take a look at the autocovariance matrix of this data, how many data do I have here? I don't know, maybe hundreds. But this is 2x2 autocovariance matrix. And what you find is the eigen value and eigenvector. So there are two eigenvalues and two eigenvectors. Now the eigenvector in the larger eigenvalue direction will give you this vector. That is from linear algebra. It's like the principal component of this set. And you add to that and you subtract from that. So that's how you split along that direction. It makes slightly better sense. It's not necessary, but it may improve the, it may speed up the Lloyd max iteration at the expense of doing some further calculations, which may slow down your overall algorithm. So it depends on you. It's up to you whether or not to use it. But this kind of eigenvalue, eigenvector analysis is good sometimes. If it is too much rounded, if the region is more round shape, not like an ellipse or with a principal axis, then of course that would be quite unnecessary and invalid. You don't really have to do that. So that is the Linde-Buzot-Gray algorithm. And honestly speaking, I also have these things written in MATLAB. So I'm going to publish them on the Mergen. I did this Lloyd max iteration, and I put an example of this Lloyd max iterator on the internet on Mergen. Have you seen that? It is there. You can download the MATLAB code and run and test for yourselves if you want. And I will also submit the vector quantization optimization algorithms that we have been talking about. So you will also have a chance to do that, to experiment, to explore a little bit. And I'm also putting a lot of help on the first lines of these functions. So when you run those functions on MATLAB, you will see how to run them. Right. Now I think it's time to it's a good time to give a break, because I will talk about other quantization methods, and I will indicate I will start discussing about the distortion metric that I have been talking about. If it's square, then this is what we do. But if the distortion that we find in between the reconstruction of the decoder and the original input, as you see, the input makes an index, and that index makes a code word reconstruction. So what's the difference between these two? If you find square error, then averaging, finding these things, or running all these things that we have seen is valid. But in image processing, for example, many people, including those who are optimizing the videos like MPEG and things like that, they use sometimes mean absolute error, which is not the square distance, but the absolute distance between two pixels or two ensembles of pixels, two regions. But then averaging will not work. We have to do something else. And there is a reason for all those things. And I will talk about those things after the break. Now, what time is it now? It is 10:39, I guess. Yeah, okay. So let's meet at 11 o'clock again. 11 a.m. Okay. Until then, I'm stopping the meeting. And if you have any questions, you may ask in the beginning of the next hour. So goodbye until then.
Goodbye.